This lesson is on the Doppler effect. Please note that this is only for CAPS, not for IEB. The diagram below is a good illustration to explain the Doppler effect. So at A, we have a sound source emitting a sound. Now these lines here represent the wavelengths or the sound that is being emitted. We note that A is moving to the left. As it moves to the left, the lines become compressed on the left side, making the frequency of these lines higher and having shorter wavelengths. Therefore, the person at 1 will hear a sound with a higher frequency because of shorter wavelengths. As this source is moving to the left and compressing the wavelengths here, the wavelengths on the right are increasing, so that now the person at 2 will be hearing a lower frequency because of a higher wavelength. This is a general rule that as soon as a sound source moves towards someone, that person will hear the sound source, will hear the sound with a higher frequency, and the person that it is moving away from will hear a lower frequency. This is a formula that can be used to calculate any of these numbers. So it starts off with the frequency detected by the listener is equal to V, standing for the velocity of sound in air, is generally 340 meters per second. However, they can give you another number. Plus or minus, we will get to the plus or minus just now. The velocity of the listener, so whether the listener is moving or not. The velocity of the sound source, so whether the sound source is moving or not and how fast it's moving. And then times by the frequency emitted by the source. This is a very important formula. It is given to you on your formula sheet. However, you are not told what everything is. So it's important to understand what each letter represents. Then we move on to deciding whether it's going to be a plus or minus in the fraction. So VL, the velocity of the listener, will be positive if the listener is moving towards the source. The velocity of the listener will be negative if the listener is moving away from the source. If the velocity of the listener is 0, if the listener is stationary, then we would just have the velocity of sound in air at the top of the fraction and no other figure here. The velocity of the sound source is positive if the source is moving away from the listener, and the velocity of the sound source is negative if the sound source is moving towards the listener. This is a very important note to remember. You are not given this in your exam. Let's go through an example because it might make more sense in this case. So we are given that the velocity is equal to 340 meters per second. This velocity is the velocity of sound in air. Note they don't have an L or S, it's just the plain V, therefore velocity of sound in air. A car drives towards you at 25 meters per second. It hoots with a frequency of 310 hertz. If you are stationary, what frequency would you detect? So now we need to note that this 25 is going to be our Vs. This 310 hertz is going to be our Fs. And this 340 is going to be our V. And we are wanting to know what VL is. FL. We write our formula down. This is 1 mark in your exam, so you must write down your formula. We then have V is 340. We are stationary, so the listener is stationary, so therefore no plus or minus VL. Then we have V again is 340. VS is negative because the source is moving towards the listener, therefore negative 25, times by the Fs of 310. You type this on your calculator and you get 334,60 hertz. Always remember to write hertz at the end. Then a slight theory question they could ask you in this. They could ask, what are applications of the Doppler effect? And these are 3 examples: the Doppler flow meter, the Doppler radar, and measuring the universe. Then we move on to the shifts. Generally, there are the blue shift and the red shift. They're the most common and probably the only ones in the syllabus. If we look at this over here, this shows the different wavelengths for each color. We start at red, moving to orange, to yellow, to green, to blue, to indigo, to violet. At red, we have a very high wavelength, but a low frequency. And this changes to ultimately become a low wavelength with a high frequency. This was taught to you probably in grade 10 and 11. So with the blue shift, we have now seen at blue, there's a high frequency and low wavelength. And this is kind of the image that they would have. At red, we have a low frequency and a high wavelength. And this is the image that you have. So when it comes to the stars and Earth, if a star is moving away from the Earth, so if we go back to this, if this is the star and this is the Earth, the star is moving away from the Earth, so therefore we are having high wavelength, low frequency. High wavelength, low frequency. That links to the redshift. And therefore, if a star is moving away from the Earth, we experience a redshift. If a star is moving towards the Earth, so if we go back to the picture, if the star at A is moving towards the Earth at point 1, then we experience a high frequency and low wavelength. High frequency, low wavelength. Then we will have, like here, a blue shift. So if a star is moving towards the Earth, we have a blue shift.